Hey everybody, it is time for trees. Well, leaves to be specific. So a while back, I was chatting with some people and they were trying to get some non-photorealistic stylized leaf shaders working. And I got curious and banged this together and people really liked it. In fact, I put it up on Twitter and it got like twice as many likes as anything else I've ever posted. So the public pressure to do a video about it has been high, but this is basically a fast doodle. There's a ton of problems with this. So I have gone and made a nicer, more robust version. And of course, since it's one of my videos, everything is completely over the top and there's a ton of features. Because let's face it, a single tree isn't that interesting. But seeing how many features we can pack into something as simple as just leaves, that's fun. I've taken this as an opportunity to just go through a laundry list of cool stuff that a lot of people probably don't know about. So I guess this is kind of a beginner's shader exercise, but I think there will be some interesting stuff here, even if you have a lot of experience. And this is specifically a stylized or NPR shading video. In fact, we only use a single shader for the entire thing, and it's not even really a shader, it's just vector math. There is not a single actual shader node in this entire thing, unless you count the transparent shader. But I also cover how to do the same exact setup with a regular diffuse node. We'll be looking at a ton of different random topics that usually wouldn't go together in any coherent sort of like curriculum, but they do go together here because it's a specific project study. We're going to be looking at coordinates and radial sphere-sized normals and leaf normal maps. We've got attributes coming from geometry nodes and attributes coming from the mesh with a geometry system. We're doing whatever this is. We're baking normal maps. We've got random stuff per face in EV thanks to geonodes. We've got surface gradients, whatever those are. We've got fake volumetric density masks. We've got the sun angle with drivers to make our shader. We've got Z-based masks, ambient occlusion, a shader that's not a shader, all sorts of crazy color mixing, absolutely terrible compile times by the time we get this far into it. We've got funky effects on the colors driven by different things, and of course at the end, alpha texture. We won't be going as far as actually doing instancing or scattering in this video, but we will be building the shader with that in mind. So we'll try to keep it compatible with that, whether you're using geometry nodes to scatter, or if you're just manually copying things with like Alt-D, you can just grab more of these, stick them everywhere. So if you're looking for a video on like how do I quickly get a stylized tree and, throw them around, this is the wrong video for you. If you want to learn a bunch of crazy shader stuff and it just happens to be using a tree as a subject, then you're in the right place. There's a ton in this file. I will be checking it up on Gumroad for a couple of bucks and sending it to my patrons. So check the links in the description. And I think that covers everything. So let's get started. We're starting from the very beginning. We have our tree. It's got a very simple diffuse material that's just white. We have a default sun, and we have a sphere that we'll be using to help test our material. The tree is split into two objects. We have the trunk and branches, which is actually a curves object that has been beveled into having this shape. And we have the leaves, which is just a huge clump of planes. The leaf shape itself will be defined with a texture. The setup we'll be covering in this video will work with pretty much any tree as long as it is mostly spherical and has a decent density of leaves. It doesn't really matter if they're alpha texture based or if you had an actual leaf model or what type of tree, but it does need to be mostly spherical. Most of what we'll learn would work for other types of trees, it just gets more complicated if you have more distinct branches. If you don't have a tree of your own to use, don't worry, it's very easy to make them. The sapling tree generator comes bundled with Blender, so you can just go enable it. Or there's also lots of other add-ons and geometry node setups and all sorts of things. There's lots of tutorials out there on how to use sapling. It shows up here. We'll take only a very quick look because this video is only about leaf shading. Under the geometry tab, you can save a preset once you've made something. So here's the tree I have saved. The important parts, I'm using a spherical shape. And then in these other areas, most of these settings I haven't touched, but I have chosen some splitting sections to have it split higher because I want this to just be a bubble tree. Same for growth. I think I've messed with a few things, but it's not changing much. Pruning matters. That has defined this curve. That defines some of the shape. And then it doesn't save leaves being on by default because you can get too many of them. Also, under splitting, it didn't save my third level of splitting because, again, that really ups the performance cost. So I probably have too many leaves, but we'll talk about that later. So that is where my tree came from, and I haven't really changed it beyond that. I have chucked this material on the trunk, and I'm just going to show it to you really quick. It's pretty simple. And we're not going to be talking about the trunk. We're going to stick to leaf shading for this one, and that's going to be just hidden most of the video. So let's take a look at where we're starting with this shader, which is not much of anywhere. It's a very simple pure white diffuse, no roughness. In fact, in Eevee, the roughness slider doesn't even do anything, so it wouldn't matter if there was. And we have two lights acting in our scene, our sun lamp and our world lighting. To get good artistic results, we need to have full control over our values and colors and understand exactly what goes into them. Right now, we've got a bunch of gray. Why exactly do we have that? Well, it's a combination of our sun settings and world settings. And we don't want a bunch of gray. What we want is for it to be black where there's no light, up to pure white where it is fully lit and facing the light source. So the first thing I'm going to do is pin my material nodes here so that when I click over to other objects with different materials, it doesn't change my node tree. Now I'm going to expand a new shader editor, but this one I'm going to set to world to let us get full access to our world settings. We can get those on the side here, but I'm going to leave that to be our sun settings. Let's expand that. And with our sun lamp selected now, we can pin this as well. So now I keep access to my sun settings and world and shader regardless of what is selected. Now let's get these lights sorted out. Our background, aka world, aka ambient light, is pure white, but with a strength of only 0.1. The color is multiplied by the strength. So, 1 times 1 is 1, 1 times 0.1 is 0.1. Also, I've got this set to show on the background, which is done here. Otherwise, we get a default HDRI, which we don't want. So I'm going to set that to nothing so that we can look at only the sun. For the sun lamp, we have several settings to worry about. What we want is for it to be pure white on angles that are facing the light directly. That gives us the best gradient of lighting. So what settings do we need for that? The color, well, it's the color. Then we have the strength. Higher strength, of course, is going to get us closer to white. And we can kind of see, if we look at this, that at some point we pass over it, where the white starts here, but it's really hard to eyeball. And the angle kind of spreads the shading more around the surface. It's simulating more ambient light, I suppose, a light source that's really far away. And then we also have all this flickering nonsense. The flickering comes from these shadows, which we are mostly going to leave disabled for this video because Eevee shadows are just kind of crap, and you probably don't even want them for something like a stylized tree. And if you do, well, we'll talk about that later. For now, goodbye, shadows. And we're going to set our sun angle to 0 just to isolate this down to just the settings we need to have a clean light gradient. So the question is, what light strength makes it so that a face that is pointing right at the sun, right at the light source, has a value of 1. And then everything else has a lower value all the way down to unlit faces. And what exactly defines an unlit face, we'll talk about later. And note that another way of phrasing this question is what light strength makes it so that a face pointed directly at the light has a diffuse shading where it is the same color as the light's color. If this was blue, This is now value 1 blue, so pure blue. And even though our diffuse shader is white, we're seeing pure blue shading. I know what strength we need, of course, but I'm going to show you how to find out. First, we'll use shader to RGB to change our shader into color data. And then we'll get a math node with greater than or less than or something where it is going to give us a mask based on the value going in. So it's black where this is not true, and it is white where it is true. So we can see that this whole area is brighter than value 1. So we want to adjust our light strength until nowhere is brighter than 1. We just want it equal to 1. So that's kind of hard to eyeball now, isn't it? So we could actually use compare instead and set it to compare is equal to 1 with a low epsilon. This is how much of a margin to allow. So now we're seeing that, like, it's something in here. We've just passed it. We're just below it or just after it. And we can kind of like start messing with this number, trying to find exactly when this is equal. We can even turn down the epsilon even more. So at the middle of that, we can see that there's a bit that is not within range. So that means we're too high. And now, I guess nothing. I guess we're about there. Does this number look familiar to anybody? What we've discovered is that the correct strength to have pure white on facing surfaces is actually pi, which you can just type pi in and hit enter, and it will give you pi to a reasonable amount of decimal points. So that is the light strength we want to work with on our sun lamp. And check this out. I'm going to put my 3D cursor at about the halfway point, and we can do pi times 2, and now we can see that the light strength being doubled has moved the place where we hit pure white to halfway in between. We can confirm that with our greater than. And if we did pi times 4, now it's 3/4 of the way. So there's a linear relationship here. So the appropriate strength of a sun lamp to give us pure white at the most exposed, all the way to black at the least, or pure whatever our sun color is strength pi. But note, this is only the case for sun lamps. For point lamps, it's totally different because point lamps have fall off based on distance. So what strength you need a point lamp to be to get you pure white at any given distance totally depends on the distance of the light from the surface and the fall off settings and radius and all that kind of stuff. But we're only working with a sun lamp here. If you're trying to do some sort of weird like nighttime scene of trees lit with like street lamps with fall off, then you're going to need another solution. But presumably, you're going to light trees with the sun. And really for most NPR shading in EV, you're going to need to work with a sun lamp because you just don't have very good controls with the others. So that's the color and strength balance. Now what about angle? What is this doing? As we turn this up, it's actually lighting further around the sphere. It's lighting faces that are pointed away from the light source. And this is kind of simulating if, instead of this just being parallel rays, if there's a bunch more maybe like ambience or bounce light. It's simulating a sky where light is actually coming from a lot of directions. Now this can be a bit weird because if shadows were enabled, this would actually be shadowing itself from the main light source. But we're not really going to worry about that right now. So we'll talk about this more in a bit, but for now, we're going to leave it at 0. Now that we've got a very basic shader working, our next problem is that our leaves are just a total mess because it's just a bunch of planes. From some angles, they look okay. From other angles, they're just black. And this is because of a bunch of issues, but mostly it's that the geometry is very simple and the normals are not doing anything interesting. We've got a mix of front faces and back faces in there. If we take a look at the normal from the geometry node, it's just a mess all around. On our sphere, it's fairly clean, but then here we've got some stuff that's up, some stuff that's down, and it's just no good. And if we go down to our back facing, we can see that on some of these, we're looking at the front face and some of the back face. We are using auto smooth and we are on shade smooth, but that doesn't really do anything when you just have flat planes. Since this is a stylized tree, we are going to use spherical normals. We're going to make the whole tree shade exactly like a sphere, which is part of why we have this comparison. I already have a normal edit modifier set up. We'll turn that on, and now when we render and look at the normals, it's looking a lot better. We can kind of see the same sphere shape. That's hard to say, but there's other problems going on. Normal edit projects the normals from an empty object. So we've got that here. We don't really need any special settings on the normal edit modifier. It's just copy. This is just the default settings with this empty selected, and I positioned it in about the middle of the tree. So if you're familiar with normals, and if you're not, you should go get familiar before continuing, you'll recall that these colors are telling us which direction a face is pointing. Red indicates how much it's pointing on the positive X. -1 on red, which is black, it would be -1 on X. And green is Y-axis in the positive direction, blue is Z. But we're seeing a lot of green on this side, where it should be negative. Like, the program thinks this face over here is facing that direction, which is not correct. We are getting this because of back-facing problems. And that is because on a mesh level, the concept of a back face doesn't really exist. That's a shader concept. And we're setting our normals on the mesh level. So if we look at like a simple plane in edit mode with normals on, we can see here's where the normal is facing. And the normal of the back face is just the opposite. It's the inverse of the normal of the front. It's going to be pointing this way by default. So when we do custom normals on a mesh level, it overrides the front face, and then the back face gets the default behavior of just being the opposite of that. But that isn't good behavior here because we're trying to have this be a sphere, and because our normals on these planes that were generated by sapling are just pointing in all sorts of random directions. The solution isn't very hard because we do have access to the back-facing. We just need to invert the normal on the back-facing. That way, it will actually be pointing in the same direction on both sides of the plane. In order to invert the normal, it's pretty simple. We'll get ourselves a color mix and set it on multiply and set the back-facing to be the factor. So where it is a back-facing, it gets this multiply. And we will multiply it by -1. That inverts the normal. And now when we turn that on, everything looks dandy. It matches our sphere quite well. I've cleaned that up, and now we'll plug it into our shader. And we have proper spherical shading. If we move our sun around, we're getting the same shading on our tree as we are on our sphere, which was the whole idea. So there are some downsides to this method. Our normals are dependent on the object location. Its scale and rotation don't actually matter. But it does mean for every tree, we need to have this object. So if we want to make lots of copies, like instanced copies of this tree, then we also need a copy of the object for every one of them. And the other downside is we lose access to the base normals, which does matter for texturing. Like if we want to use a leaf texture for a normal map or something like that. It doesn't matter for UVs, but it does for normal mapping. So we'll be coming back to this later as well, and looking at other options. Now that the shading doesn't look quite as terrible, we can talk about the world lighting. For now, I've set the sun lamp to 90 degrees on X and Z, which is pure horizontal lighting, as that makes it easy to see what we're doing. So the world light, how exactly does it work? How does it interact with everything else? It is actually very simple. Whatever we're getting out of this is added to our shader. So here is a light strength of 0.3, because 1 times 0.3 is 0.3. And this is exactly the same as doing this. That. And that are identical. And actually, since we've done a shader to RGB, it's also identical just adding with a color node or even using a math node. It's all the same thing. And since that is identical, we can even do this. Instead, we can subtract and completely cancel out our world light. We can still see it in the background. So that goes up to 5. This will need to go up to 5. And this holds true even if there's color involved. Like, let's set that to be full blue, and now we will subtract 0.5 times blue from it, and we are back to our black to white. So using the world light at all is exactly the same as adding that to everything in your scene, and you have no way to control or stop it, because this is just built into the diffuse shader. We don't have a way to tell the diffuse shader to not be affected by the world light. We could cancel it out like this after, but that's a bunch of extra work and extra compile time and processing. And you can also cancel out the sun lamp as well by dividing by the sun color times normalized strength. We won't get into that because you just shouldn't do that. There is a better option, and that better option is the light path node. This is a node that does a lot more in cycles than it does in Eevee, because in cycles there's all sorts of light bounces and tracking light, but it still does some things, mostly these top outputs. IsCameraRay gives us a mask of if something is directly visible to the camera, which is another way of saying a mask between direct and indirect. So if we mix between two things based on this, then the one in the second socket is the one we actually see visually, and the other one is what's used for indirect things like light. So this lets us, say, have the light cast by the world be a different color than the light visible on the world, or more importantly, it lets us set it to 0 and just turn it off completely. So this is the sort of setup we use if we want to be able to control our background color or like put a texture back there or something, but not have it affect our shaders at all. Now again, this isn't something we can control on a per material level. That's just a limitation of Eevee. In other engines like Malt, we can, but this is just how it is for now. You could, of course, delete the world entirely over here, and that's the same as just choosing black. So we're not going to go quite that far. So here's a handy node group I use, which is just this IsCameraRay mixing between different color and strength into one background shader. This isn't really different than mixing between two background shaders. It doesn't really matter. This just happens to be how I set this up. So this just makes it quick and easy to choose what our visible and direct and indirect settings are. Now, why is it so important not to have the world color interfering with our shader? I'll give you a quick and easy example, which is if we wanted to do something like a toon shader. Generally, a toon shader is done with a color ramp like this, and you do some amount of ramping to squish your shading into a narrower band of some sort. And this is based on the input black and white. So as soon as you use any amount of indirect light, you're changing what your original gradient values were, which means you're going to be changing your toon shader relatively. And that can get really weird depending on what your light is, because like colored light is effectively weaker, because RGB 111 equals value 1, which is what's going to be used here effectively. Whereas if you have less than that, it's the same as lowering the value. So what this means is that as you use the same asset in different lightings and different scenes, it doesn't change how bright the lit area is, but it changes the size of it, and it can change them in really wacky ways. So it just doesn't work. You need a consistent, normalized black and white shading gradient if you want to do a ramped toon shader. Now, we're not planning on using toon shading for this tree. You could, but I'm not going to because it doesn't need to be that complicated. But we are going to be using our shading mask for various things. Here is a quick example. We want to have different colors in the lit areas versus the shadows. So I'm going to pick a green here. This can be our main tree color. And then where it's going into the shadows, we're going to have it get a bit blue. And then we need to get our shading back, which means multiplying that by the shading color. And now in the most lit areas, we have our trees green, and then it shifts towards blue in the shadows. Coloring shadows like this or doing hue or saturation mixes is a really common part of stylized art. So we want the capability to do this. And again, once we start doing this, it's going to change it. And maybe that doesn't matter, maybe you want that, but if you want it to be consistent, then we have to have that normalized shading mask. All right, but what if you do want world light still? Well, it's not too hard to just do it in the material and ignore the usual world settings. So here I have a node group in the world nodes, and I'm going to connect all of these up. And all that's happening in this global values group is that I can set all of these parameters in the same place. And that means I can copy that and put this node group in my shader as well. And we did already mention the math involved here. It is color times strength. And then it is just a matter of adding that in before we multiply by our actual material color. And I'm going to disconnect it here and leave these at nothing. And now, whatever I set in here, it's exactly the same as using the world, but only for the materials I've set this up in. So that is how we easily get material level control over world color and strength, but there are other aspects of using the world that might not be so simple. Like if you want to have it affect glossy reflections or more complicated stuff, it can get quite complicated if you want that to be global, because the world maps things in a certain way, and then you have to map those onto the objects the same way because this is material level, and it's a whole hassle. So usually when doing NPR, you're already not using the world, but if you want to use a tree like this, or like use the shader in some scene where you're doing like stylized PBR or something that does use it, then you need to be aware of these issues. For now, I'm going to move forward assuming that it's only going to be our own material level world or ambient lighting. Which means for now, this is going away, but we are going to come back to some of these options later. Let's return to the sun angle setting. What exactly does it do, and do we want to use it? The default behavior at 0 is that faces facing the light are fully lit with value of 1, and then it's a gradient down to perpendicular faces which have a value of 0. They're not lit. And everything beyond that that's facing away is also 0. As we turn it up, we can see that more faces are getting illuminated, even ones pointing away from the light. But the strength of the illumination is lower. In fact, it has halved. And an easy way to check that is we can use our world settings and set the background to 0.5. And now it's easy to see 0.5 on the background, 0.5 on the sphere. So that's just a quick way to compare values. So our light is broader, but weaker. If we wanted it to still go all the way to 1, we can multiply the strength by 2, and now it does. Or if we were leaving the strength at the same amount, we could do the multiplication in the shader with a math node. And there we go. This would matter if we had other things in the scene that were using the same sunlight and we wanted, I guess, different values, although generally you shouldn't have a situation like that. Okay, so do we even want this effect? Should we be able to have our sunlight light up things that face away from it? Well, normally I would say no, but we are doing non-photorealism, and that means anything goes if it matches the style. But even within the realm of a fairly realistic style, in this use case of the tree, I do want this effect. And the reason I want that is because we are doing a stylization of a complex object that light can actually pass through. You know, in a real tree, light doesn't just end halfway through, so it can pass through the leaves and branches. It doesn't occlude like a hard sphere. And if you were drawing a tree, you also wouldn't have it be so, severe. Light doesn't just stop halfway across it. So this is a way to let us kind of get a visual style that implies more light passing through without doing anything very complicated. So it's a subjective stylistic choice, but I think it's a good one in this case. So even if we have the angle at 180, we can still use a map range to choose where we want our terminator to be. We can change it back to the old behavior or have it only be 0.4, 0.3. This is kind of like a toon shader now. So if we knew we wanted this option available to everything in our scene, then we just set our strength to pi times 2, set the angle to 180, we don't need this multiply, and then in all of our shaders, we use a map range to choose how much of this we want. So it's effectively material-based angle. But if this tree is going to share a scene or lights or anything with any other sorts of materials or like PBR stuff or anything where this is a problem and you don't want to put it like in its own layer or scene or something, it would be nice to just have this be completely independent of the sun. So we're going to look at a bunch more options to get diffuse shading. Let's understand how our diffuse shading works in the first place. So down here I've got our normals again, and I've got a dot product node. And, well, that looks like diffuse shading, doesn't it? What's going on here? And this has nothing to do with our actual light. This is pure math. We are calculating something based off the normals and the direction from this vector input. And we can change that to something else. Now it's a light facing down. And that's because what shading is a calculation comparing normal angle to light angle, and then color and strength multiplies that. This dot product calculation is actually part of our diffuse node. It's a key part of all shading, I think. And what it is a comparison of two directions. One direction is our normal, which is a different value in different places on the model. So, on this side of the sphere, it's mostly 1x, and, over here, it's 1y, and then it's some mix between along the curve of the sphere. And our dot product angle here is just 1 on x, which is this direction down the x-axis. So the dot product compares these two angles. If they are pointing in the same direction, like this part of the sphere is pointing on x-axis, then you get 1. If they are 90 degrees to each other, you get 0. And if they are negative angles, you're actually getting negative values all the way to -1. We cannot do this for our regular diffuse node, because it doesn't have the values below 0. It's been clamped at some point, which is the same thing as if we threw a clamp node in here. Clamp eliminates all values below 0. Everything below 0 becomes 0, and everything above 1 becomes 1. So we cannot stop the diffuse node from clamping because we don't have access to its internal workings. If we did, we would just do that, and we could, get around a lot of these problems. So the reason we have to do this sort of like light faking and all this stuff is just because EV is hard-coded into certain options. Whereas in Malt, we would be able to just make a custom version of our diffuse shader that exposed these options. So just creating our shading out of vector math has a lot of upsides. We get more data from it, and we're completely disconnected from the regular light and world systems and all that stuff, so they can't mess it up. It's really handy for stylized shading. But there are downsides. We cannot get cast shadows at all, but we probably don't want them on this tree anyway, so that's not really that much of a downside, and EV shadows are awful, so they're basically unusable in my opinion, so whatever. But it might become a problem if the shadows ever get fixed. So the other downside is that we need to build our own controls for these lights. We can still sync them up to some object, including this same sunlight, so let's do that next. We're going to need to get the current rotation of the sun lamp, and we can do this with drivers. You can copy this new driver and paste these onto a combine XYZ. This may look a bit odd because I am copying 90 degrees, but when I paste, it's showing 1.571. But that's because what it's showing here is radians instead of degrees. All rotation math in Blender is actually done in radians. It just converts to or from degrees for the user interface to make it a bit more human readable. So we've got the sun rotations now, but we cannot just plug that straight in. This is giving us 45 degrees down from the right. And as we adjust the sun, it's always going to be a bit off unless we go to 0. But wait, 0 is nothing taking place at all. The problem is that these rotations are not the angle of the sun. They're rotations on top of its starting position to get to the new angle. So it starts facing down on z, which would be -1z, and then -1z rotated by these amounts is the sun vector. So let's get a rotation node. So -1z, that's the original vector. Then we will rotate that by, we're going to need Euler. And we won't need the center, so we'll just... Okay, now that is moving correctly, but it is inverted. The reason it's inverted is, remember, dot product returns 1 when the vectors are in the same direction. And right now the sun is pointing this way, and, you know, these surfaces are pointing that way. So they're pointing at each other, not in the same direction. So we're actually going to invert the starting position, and now it works correctly, even if we return the sun to 0. So that's the sun lamp working, but remember, this could be done with any object. An empty something else doesn't have to be the sun lamp. And it doesn't even have to be a lamp or an object at all. The normal node lets us just get a direction vector, and we can rotate this sphere in the node itself and control the light angle that way. Now, this is a bit counterintuitive because the default is this assumes you're looking straight down on it. So we're looking at, you know, wide of the sphere, but it's actually shading on the bottom. But we can correct that by rotating it 90 degrees on X. And now it's going to match up with what we see. And the second one is input only used for dots, so we can actually just hide that. Another neat feature of the normal node is that we can do this in a group and use it to create that normal sphere as a group input. That's plugged into this other socket, so we just don't need this node anymore now. But if we don't have that node, we do need to add a vector math normalize in order for the rotate to work properly. So if you wanted to have a big node group for this tree in the end and just control the light angle completely in the node settings, you could do it with this. And of course, you can just define the angle with a vector input if you're familiar with how to do these. This is 1 on X, that's facing up on Z, you know, facing down on Z, etc. So you have a ton of options. You can really do it however you want. I'm going to stick to the sun, the driven value for now. But to make it a bit more convenient, I'm going to bring back the global values group, and I'm going to copy this node and stick it in here. And that deletes the drivers, so that's a hassle. I don't want to have to recreate them. But there is a trick to get around that, which is you add the node to a group, and then we copy the group in here, and then we disband the group, and now we do have our drivers. So that's how you copy a node with drivers. I guess that should be sun rotation, not angle, technically. And I've chucked it in a node group and named it Lambert Shading, because that's the name for this. Next, let's make it so we can control the angle. So we start with our original shading with the terminator in the center, and it goes all the way up to 1. If we add to it, now things are too bright, but it goes all the way. So we multiply it by 0.5 to make it 0 to 1 again. But if you recall, the actual sunlight angle when we turn it all to 180 is 0 to 0.5. So if we only multiplied it by 0.25, we would have that. But, you know, we don't really want that for anything. So we'll leave that at 0.5. Now we want some sort of mix for the angle, so we could just use a mix node between this and this. But what if we wanted our terminator to be more in this direction? This won't let us do that. Our next option is the map range node. Right now, it's not doing anything because our input is 0 to 1, but we can tell it to treat it as if it was 0.5. Now it's in the middle, or we can go all the way up here. So that gives us a good range. This is basically the control we want. And actually, if we're using the map range node, we could just bypass this other math entirely and tell it -1 to 1. because that's effectively what our original input is. There is data in this black here, it's just below 1. And if you remember, the map range node lets us basically tell it what the input range is and maps that to an output range, and it's doing a bunch of math to do that. So this does let us do the right thing, but what I'm looking for here is to have a node group input that goes from 0 to 1, with 0 being over here. I don't want it to be -1 to 1. So we will keep our add and multiply. So the map range node is solving our problem, and I could just make a group input of from min, but we're not using a lot of the features of the node. So let's just actually make this out of pure math so that we can understand what's going on here. So our goal is to have it so that when an input number is at 0, things look the way they are, and when it's at 1, we have scrubbed the gradient all the way to the right. I guess actually everything would turn black when the input is 1, which is what it was doing on the map range node. We've already adjusted the range with add and multiply, so we're going to need to do further addition or multiplication based off some input. So we know that adding effectively moves the terminator, the point at which everything is black, to the left. If this is -1, 1, then as we add to it, we are remapping this to be 0 to now 2. That's why we need the multiply to bring it back into the range of 1. So to move it back again, we would use subtraction or negative addition. I guess it's worth noting that this multiplies by a decimal value, so technically this is division. So if we subtract 1, then, well, actually that did the job. Let's make our input there. We subtract 0, nothing happens. As we step this up, we can see our terminator moving. So that's actually pretty easy. Once you subtracted 0.5, we're back to where we started. But this isn't going to 1 anymore. We're now 0.5 to 0.5. Well, we're 0 to 0.5. So we need some multiplication to restore the top end to being 1. We multiply by 2, then that is correct. So when we're subtracting 0.5, we want to multiply by 2. So how about if we're subtracting more? Like let's do 0.75, and now we need to be multiplying by 4 in order to have it be the right amount. So to complete this, we need some relationship between 0.75 and 4. So what's the math where when a value is 0.5, we get 2. When it's 0.75, we get 4. It would be this. We subtract our value from 1, which is inverting it. So now this would be 0.25. And then we divide 1 by that amount. So 1 divided by 0.25 is 4. Or if this was 0.5, it would be 0.5. 1 divided by 0.5 is 2. And now we have the desired behavior, where as we step up from 1, we get a full gradient across. So our brightest point is always white, and our darkest point is always black and never below, and we control where the terminator is. And that is what is going on inside of the map range node, by the way, if you look up the math there. So now we will make this a group input. And we will set that to default to 0.5 with a min of 0 and a max of 1, and we will call it terminator. Maybe terminator position. And now we can scrub that. Now this control we've made is 0 to 1, and that is different from the sun angle, which is 0 to 180, and actually 180 on the sun angle is our 0. So if we did want this to take a angle input and work exactly like the sun, then we would remap this. If you wanted that behavior instead, you do math like this. We're taking an angle of 180, we're dividing it by 180, so when the input angle is 180, then we'll have 1. We invert that, and then we multiply it by 0.5. So now when we scrub this, 0 is 0.5 on our gradient, and then 180 is our 0 in our previous one, or 1 or whatever. Anyway, it's the same behavior as the sun. And we could even keep going and remove our multiply, that is putting this to 1 and have this be 0 to 0.5 like the actual sunlight. And we could add a strength value and make it so that, a strength of pi equals value of 1, and higher than pi multiplies it, and lower than pi divides it, but multiplies it by less than 1. You could completely recreate the exact behavior of the sun lamp if you wanted to. But all of that is just adding extra nodes that we don't really need. So that's why I just choose to directly pick the terminator position as a value between 0 and 1. And now I have cleaned that group up and given it some labeling. And I'm outputting both the full range and our shading mask after we've chosen our terminator position, because we might want both. Since we're on the subject of faking shading, it's a good time to mention another thing that comes up a lot in NPR rendering. I'm going to turn on the ground plane I've got here, which is just a diffuse shader. And it's not really getting any light right now because the sun lamp is not angled down. So often we have a situation where we want to have something like a tree cast shadows on the ground, but not receive them themselves. And currently, if I turn shadows on, we're getting that. So this is just another benefit of using this method. We still have to set our shadow mode to opaque or alpha clip or something. Doesn't really matter right now, but we'll have to think about that when we start adding transparency for our leaves. But yeah, so this is just a perk of using fake shading. Before we move on from shading, we'll look at one more example, because I'm sure somebody out there is going to want to fake their sun angle and control it in the material, but not want to use entirely fake shading. So is there a way to do that with diffuse shaders still? And the answer is this. So we have a regular diffuse shader, black to white, cut off at the usual spot. Then we have a second diffuse shader, but all the normals have been multiplied by -1. This inverts them. So now it's lighting in the opposite direction from the light. That gives us shading information below the usual cutoff point. We can then remap that into something we can use. We've flipped it from 0 to 1 to 0.5 to 0. So now we have black to 0.5 ending here. And then on our first one, we're flipping it to be 0.5, 0 to 0.5. Then if we add that together, we get the full 0 to 1. So that gives us the same thing we've been working with in our Lambert shader. And we could then add the same like remapping and terminator position and all that. But of course, since we're back to using actual diffuse shaders, this is now subject to light color and strength and world lighting. And if we try to use this with shadows, it's a total mess because it's going to self-shadow, and that's going to mess up all of that. So I'm going to stick to the fake Lambert shading. Let's get back to our color mix setup. So before, we were mixing between our two colors based on the shading, and now we can do that, and we can move the terminator position. So in this setup, areas that are darker are more blue, and areas that are lighter are more green, and we're moving where those areas are. But what if we wanted it to always be blue in this side, rather than blue wherever it happens to be dark now? That's where we can use the original shading gradient to get a different mix. So now, as we move with the position, we're revealing more of the blue. Now, is this an effect you actually want? That's up to you. That's a subjective artistic choice you can make. And we don't have to have it just be the original gradient. We could say choose different terminator positions for the shading mask and for the color mix. Now, I do like this effect, and you'll start to see why as we keep building this up. So we're bringing in some fake indirect light now, and we're adding it only into the shading mask. And it doesn't look quite right because we need to go back into this group and clamp that. And while we're here, let's clamp that for safety. So now we don't have anything going to full black because we're adding light. And that means we are revealing that color gradient in the shadow areas as well. So that's the reason you might want to have it. This is still moving our lit gradient. And at this point, I think it's time to chuck this all into its own group for better organization. To save some time, I've just gone ahead and set up the group, and now I will tell you about it. First of all, I have removed the Terminator position control from the Lambert shading because I want to have two of them. So I'm going to do it in this new combine colors group. This looks like a bunch of stuff, but it's just the things we've been working with. So first of all, we get our shading gradient and the Terminator position, just like before. And we control that. We have ambient light, color, and strength, like we learned about earlier for the world group. It's light times strength. This doesn't really need to be clamped. They add together. That gives us our shading mask. And then down here, we are picking a different Terminator, which is the same input, but multiplied to be 2/3 of that. And then that's the mix between our colors, and we multiply the shading by the colors. So now as we adjust our Terminator position, we're always going to have a bit of a blend between our shading color and our full color, unless we disable ambient strength entirely. We've still got a little bit, but we're not seeing the full thing. But for a tree, you're always going to have like 0.1, maybe 0.2 ambient light. Higher than that, probably not. But yeah, that's a pretty safe bet. Even for like a nighttime shot, usually instead of letting things go full black, you would just tint them even more blue or something like that. But again, artistic choices. Speaking of ambient light strength, it can go higher if we're using a color other than white, which you might be if you're trying to, like tint the shading something for whatever reason, for a different day or for some atmospheric effect. But keep in mind that as you go to the edge of the color wheel, you're reducing some of these values to 0. So it actually gets darker. Like near the center, it's bright, and now by the time we get to pure red, it's really dark. In fact, the ambient light isn't doing anything right now. The reason for that is the way the color math works. So here, we've got our ambient light, which is red. Red has essentially replaced black in our shading mask because we've added red to it. So in areas that were already white, white already contains red, so those values are probably above 1. But in areas of the original mask that were black, there's nothing there but the red that's been added. So in our light pass, everywhere is at least value of 1 on red, and then some areas also have blue and green, totaling up to 1. Then in our color mix, we only have blue and green. Red does not exist in our color. So the problem is we then multiply them. And if you remember how color math works, it is each component of this does the mathematical operation on the corresponding component here. So in this case, we have the red here is being multiplied by the red channel here, which is 0. So anything multiplied by 0 equals 0. And then up here, we do have some green and blue multiplied by green and blue. But our red is completely canceled out because there is no red in the color mix. If we come in here and we add even a little bit of red in, then suddenly it appears. Because there is something to multiply, it's not just killing it. So this is something you need to keep in mind when choosing your colors. Now we could use a different math setup and mix shadowed areas to the ambient color instead of multiplying them. That could get you around this problem. I'm not going to do that in this case, but if you really want to have super boosted ambient colors, that is an option. Moving on, we also have to watch out for what color we choose in the shading color. If we choose something darker, it can totally ruin our value balance. Or if we go to saturated or something, things can get weird. Mostly it's a matter of value. So let's put something in to keep that from going crazy. The goal of our shading color is to tint the main color of the tree towards something else in the shaded areas, not to totally take over and clobber it. And there's lots of ways we can set this up. Right now, we're using a straight mix to another color, but we could also do something like a hue shift with HSV. The HSV node makes relative changes to your colors. So right now, nothing has happened even though I've put in a factor. Nothing happens until I change one of these values. So if we change value, it's going to get brighter. And we can see it's gotten a bit brighter there. It was already really bright. So this is multiplying the current value. When it's at 1, that's multiplied by 1, or we can turn it down and go all the way to 0. Then saturation is boosting or reducing the saturation. Lower saturation tends to look lighter. It's going more gray. and then hue is going to move the hue from wherever it started. If you're not so familiar with these concepts, here's how you can see it on the color wheel. When we have no hue and saturation, we only have value to work with. Value is its own slider. But what hue is doing is, as you move hue, it's moving you around the outside of the wheel. With 0 is red, and then also 1 is back to red. So if you start with a hue, let's say here, and then you're adding or subtracting from it, then you're just getting whatever is to the right or the left of it on the color wheel. And the saturation slider is moving towards the center of the color wheel, which brings you towards white, or it brings you towards just being whatever the value is. So we could just have our color shift be HSV. We do need to invert this because otherwise it's changing in the lit area and we want to change in the shadow area. So if we did this, here is our same shift to blue in the shaded area. The problem is if you want to use this setup where your input isn't necessarily going to be green. In the case of this tree, well, trees pretty much only come in like green, although, a bit towards yellow. Unless it's autumn, and then you might want, say, like orange or red leaves. So do you want those to shift to blue? Maybe not, maybe yes. Do you want them to shift to green? Right now, our HSV is just shifting this way around. Whatever we input is shifting clockwise, I guess that is. So if we want it instead to always shift towards the same place, then the HSV node is not the right tool for us. So we could do something like this. We can separate HSV and get those values isolated and then recombine them. And that means we could do some mixing in between. Like, say, mix our hue to always be towards 0.5, which is right between blue and green. Or we can go lower. Let's see, higher. Looks like it's clockwise. So there's the hue for light blue. So now, with a setup like this, no matter where we start, it's always mixing towards blue, which can get pretty crazy. So, I'm not sure you do want this, but that is a different way of doing this mathematically. And of course, if we do want to pick it with a color wheel, we can just have it mixing towards the hue from our other color. So now it's only using the hue from here. It's completely ignoring the saturation and the value. So that's probably, I think that's about the behavior I want. But there is a better way to do this without all the separating. The mix node already has the option we need, and it is called hue. What this does is you choose a color in input 0, and then that color will get mixed based on the factor, which is our shading, towards only the hue from input 2. So we can see as we move the hue around, it is mixing to that hue. But the saturation and the value do nothing, unless the value gets so low that it makes the hue not do anything, because it is multiplied by the value. So this is perfect if we want to use only the hue from our second color. Except we need that the other way round. So again, we would need to invert the mask. There we go. Now that is working. We also have the same options for value, saturation, and color. Color is saturation and hue at the same time, but not value. Like if we want to change that to color, now when we adjust this, our saturation does work and our hue works, but the value does nothing. So I think that's actually the one I do want to use. But again, this is completely subjective, up to you. This is the actual making artistic choices part of all this. So there we go. That is our color mix setting, all done. And now I will maybe get a bit more ambient light, and we shall continue. Our next topic is the glossy shader. That's another usual part of any shader setup. So it, highlights where the light is hitting more, And gloss is different from diffuse because the brightest area has to do with where the light is hitting, but also it's dependent on camera. So notice now the brightest part is, there. So basically the hotspot of gloss has its size determined by the roughness, its size and strength, but the location is like halfway between where you would expect it to be brightest in diffuse shading and the gradient of the normal on camera position. So we could make a completely math-based version of the glossy shader as well, but we're not going to, and we're not really going to talk about gloss because it's just not really necessary for a tree. Artistically, I do want some sort of effect like this that changes things based on more light. We've got a bit of that here, but this is all a bit too linear. So I would like to brighten it or something, but it's not really necessary to use gloss for it. Since the tree, isn't shiny, like leaves are shiny, but the whole tree shouldn't have a hot spot. So if I did use gloss, it would be very rough. And then when it's this rough, well, I've already got a shading gradient. I might as well just ramp that again or whatever. So that's what we're going to do. My alternative is that I am going to use a HSV node to do an effect. We're also using a map range node this time because we are doing something a bit more complicated. So this is a very subtle effect that's not easy to see here, but I'll turn it up more. What this is doing is in areas where the incoming mask is 0, we are setting the saturation to 2. So that is making it more saturated in the dark areas. And the areas where the incoming mask is closer to 1, it is desaturating it. So I'm not quite sure how much of this I want, but you can see that. And since saturation tends to lighten things because you're kind of mixing back towards the value, then it is giving me the net effect of lightening things a bit based on how much incoming light there is. Now you can see that more. I think that's a bit too strong. Now, the impact of this really depends on what colors you're putting into it. And that is because, again, the HSV node is relative. So if you start with a very desaturated color, like, there's like hardly any saturation here, then there's not a whole lot of a difference on that part of it. Whereas if you're starting with a color that is super saturated, then you're going to notice it a lot more. So we could instead use a mix more like this, but I think this will be fine for now. I haven't gotten into any trouble with it yet. I think I'll go with 1.5 and 0.9. So it is definitely a subtle effect. But it's just enough to break up the linearity a bit. Goodbye, gloss node. If anybody is really curious about doing fake shading with gloss, then feel free to message me. But if you're getting so much into shader math that you're interested in that kind of thing, just go use Malt. That is my advice. All right, so what comes next? I think I'm pretty happy with our shading options and our color options. And now we have a couple of obvious flaws. One is that everything is still just squares, so we need a leaf texture. And the other is that the whole shape of this is still a bit dull. If we zoom out enough, this actually works okay, even with no leaf texture. Like if this was going to be on a bunch of hills way in the background of like a landscape shot, then we may not need much more than this. We may not even need this. You could probably just do a flat color mix and, whatever. But yeah, I guess we can do a leaf texture next. I've got it in its own group, and let's hook that up. And now we have leaf alpha. Nice, this is getting interesting. And at this point, I'm also going to hide our trunk because it doesn't really have anything to do with anything. We'll bring that back at the very end. Inside this group, we've got a few things going on. We have the actual leaf texture, which looks like that. Or perhaps this would be a good time to get the image editor. Ooh, sneak peek there. Actually, we have 4 different leaf textures. They're slightly different. And what we have going on here is that we are picking a random one off that sheet of 4 so that we have some variety. And we're doing that based on a random attribute coming from geometry nodes. That's over here. If I turn that off, then they're all set to the same one. And then we have the actual mix based on this leaf texture. It's not using the alpha because this is just a black and white texture, so there's no reason to put it in the alpha channel. So that is mixing with our shader and transparent. For that to work, transparent alpha clip needs to be enabled for the blend mode. And for it to affect shadows, it needs to be alpha clip on shadows. We looked at shadows earlier. And then over here, we are exempting our test sphere because I don't want it to get the leaf texture on it. Otherwise, we have that. The way that's done is in the object relations of the sphere, I've set it to have an object pass index of 1, whereas the leaves have 0. So the object info node is bringing that in. So now we can see 0 and 1, and we're mixing to just have the shader and not have that transparency, because we want our sphere to keep working as a proper material preview. And with the leaf texture on it, it's a bit difficult. So where did this leaf texture come from? How do you make one for yourself? Well, I modeled it in its own file. This is pretty straightforward. I modeled one set of leaves here, and then I duplicated that 4 times. I have some displacement on there, and I use proportional editing to give them very slightly different shapes, just to bend them different ways. I'd like to have some more variety, and it's not a very good leaf, but it's good enough for this tutorial. And then we have a camera, which is set to orthographic. The scale is 1, because I've got this reference bounds object, which is 1 by 1. Each of these leaves is, within that. So then we've got a black background, and you just hit F12 to render it, and there is your leaf texture, and then you just save that out. So that part is very easy. And there's all sorts of stuff you could do to generate procedural leaf textures. I only did 4 different ones. You could have a lot more than that. And I guess these are leaves, kind of like a bunch of them on a twig. I thought that was appropriate for this tree. If that is or not for you depends on how you make your tree. The next is our Randomized UV tile, which is more complicated. We want each leaf to get a random 1/4 of that texture. And there could be a lot more than 4, but that was enough to demonstrate this. So we have a UV map of the leaves, which was generated by sapling. And we have a random value per island coming from geometry node. Now, ideally, we just use random per island from the geometry node, but if we go down to that, it doesn't do anything because it is not supported in Eevee. That only works in cycles. We have to use geometry nodes for this, but that's not a big deal at all, and we'll look at how that works in a minute. For the randomized UV tile group, we're going to take a quick look through it, but we won't spend too much time on it because I already have a whole video about how to do this. Here's the article on my blog. There's the video. I'll put the link in the description. That explains how the whole thing works, and with a more complicated setup than I'm using here. Although I think in that one I didn't account for random per island not working in Eevee. The use case in that video was based on every different piece being a different object. So it doesn't matter now, though, because we have geometry nodes. So let's take a quick look. The core of the group is the Get UV Tile group, which is covered in that video. This lets us split our UV map into columns and rows and pick which one we want. And then we feed random numbers into that based off our random per island and based off random per object, in case this was being done on an object level, or for when we duplicate and instance the tree. So there's our random per leaf, and here is a random value for the whole object. If we duplicate this, that has a different one. We combine them. In this case, there's a lot of ways to combine different random seeds. In this case, I'm adding them together and then using a wrap. What wrap does with these settings is it makes it so when you go over 1, it wraps back to 0. So a value of 1.1 inputted would give you 0.1. So this way, our random value always stays between 0 and 1. That's not the only way to achieve that. I just thought it was cool and that I would tell you about the wrap feature. So then we've got all this other math, and what this is doing is taking that random value between 0 and 1 and making it a random value, well, making it 4, 1, 2, 3, or 4. Or it might be 0, 1, 2, or 3. Anyway, It's doing some comparing and addition, and this is all also covered in that other video, because it needs to be formatted into columns and rows in a 2x2 grid. So once all that is done, then we do end up with a random one off that texture. It would have been easier, I guess, if I had it be 4 in a row instead of 2x2, but, you know, whatever. I already had this setup made, so I just used it. And the point of using a group like this is that this can scale to any amount of rows and columns we want. So if you are interested in setting up a randomized texture, go watch that other video. For now, we will move on. Here is the random per island geometry nodes group. It's pretty simple, but there is a bit to explain here. So the random value node, it gives us a random value between two numbers. We can choose what type of thing it gives us. And what we need to pay attention to is the ID and the seed. We want to make sure there isn't any ID being used for something like this. And the seed I have plugged into the group input so that you can change it here. This way you can choose the pattern of your randomness. So seed is what you feed into the random generator, and as long as you have the same input seed, you'll always get the same outcome. So the question is, how do we have this be random per face instead of per vertex or edge or whatever? The random value node doesn't control that at all. What controls that is whatever node is calling it. If you've watched my other videos on geometry nodes, you'll be familiar with this. But basically, you follow the geometry to see the order of execution of the tree. So our geometry comes in, it hits the store named attribute node, and that is looking for a face attribute. And so when it gets to this node, then it gets the random value for whatever domain is in use on this node. So if I change it to point, it's now random per vertex. If I change it to, you know, well, edge, you're not really going to see much because it's going to interpolate it back. But basically, it is what we choose here that defines if it's face or vertex. And here we set the name of an attribute to save this all to. And I've named it RNDM face. And this will create the attribute even if it doesn't exist on the mesh. Like in the attribute section, nothing exists. It's being made by the GeoNodes group. We don't have to assign an output. We could output this instead and do it that way, but the store named attribute node takes care of our face selection as well. So this is all we need. And then we use an attribute node here. If you have attributes on a mesh, they will show up here. But since this is being made by GeoNodes, we have to use the attribute node and manually enter the name here. And then I've just hidden the rest of the node. So that's it. That's all you need to get random attributes per face in Eevee. Okay, it's time for the next rabbit hole. I'm pretty happy with how this is progressing, but it is a bit bland. It's fine to shade the tree like it's a sphere, but if it's too clean of a sphere, it's just, well, it's a bit bland. I want to get some more shape into that, because, you know, we've got lumps and branches and all that stuff. I'm going to show a bunch of different ways to improve the detail level, but before we get into them, we have to first deal with the way we're defining the shape of the tree, because they're going to be based on it. And by that I mean the normals. Our current method of getting our spherical or radial normals with the normal edit modifier and an empty object works fine, but it has some limitations and it gets in the way of other methods, and it doesn't duplicate that well. I do want this whole tree to work when being instanced. So we're going to get into how these radial normals work and how they're made, and our other options for making them that will behave a bit better. And the first step is to understand exactly what behavior we're getting right now. So currently, our normals are being projected from the point the empty is at. So its location matters, but its rotation does not. Its scale, though, does matter. If we scale everything, there's no difference. But if we scale only one or two axes, it's going to be like squishing this. That's pretty easy to see up here. We scale that down. Or if we scale the tree object, notice it's changing a bit too. If we rotate the tree object, then we move it away. If we rotate them together, then I gotta do that around the 3D cursor. Then it works fine. We can see that we still have Z is up, because remember this like sort of cross we can see is our axes. It should be staying consistent even as the mesh moves. And if we rotate it on Z, the normals stay pointed in the right direction in world space. And that's important because if you were duplicating this tree and instancing it, one of the ways you would stop people from noticing that you're just reusing the same tree asset is by having like randomized rotation. And one of the problems, as I mentioned earlier, is when we do start duplicating the tree, well, that's running off the same object. So this is normals projecting from here. So that's no good. We need to duplicate it with the empty object, which is adding an extra level of objects we need to keep track of. So, that does work. But it'd be nice if we didn't have to do that. And actually, we don't. We don't need the target object at all. We can have the object use its own origin point. The problem is it's down here. If we had kept the empty object and moved that to 0, that looks the same. But the modifier does come with the option to offset where it thinks the origin is. So we can look at this empty and copy its height on Z and put that in Z. And now we have the same thing as we had with the empty. And again, that's working all right on the Z rotation, but there's a problem when we do other sorts of rotation. It's at an angle. It's wrong. And this is something to do with how it's doing the offset math and its order of operations. So this doesn't actually work that well if we want to have a little bit of rotation in other axes, which we might want to have. Or maybe you don't, but I still want you to understand how this stuff works because all of these concepts apply to other things as well. So our first alternative option is to instead make these radial normals in the shader. We can get the object coordinates of the same empty object, but they aren't a normal yet. What we're looking at here is the object coordinates, and coordinates are position, whereas normals are an angle. And of course, we run those through the normalized node, and then we do have basically the same thing. There's some very subtle differences because one is mesh calculated and one is shader calculated, but we're not really going to worry about that. You can check this differences between vectors by plugging them both into a distance node. So you can see black is where they're the same, and white would be white would be one distance, one away, because it's getting you it's comparing the locations in space. So yeah, this isn't very bright. There's only very subtle differences, which I think just has to do with linear interpolation of normals. So effectively, this is the same thing. You won't be able to tell the difference visually. So the coordinates, though, because we don't just want normals, we want coordinates of our tree so that we can do things with it. We'll get into what later. But that is what we have. What we're seeing here is this is the distance on the x-axis from the center of the object. So 0 up to 1, and then it goes greater than 1. So it's a distance in actual units in space. It is not normalized or anything. So that's useful for various things. So by using this method, we are getting both a normal and a coordinate. With the modifier, it was giving us our normals, but we'd still have to go get the coordinate from somewhere else. So we might as well make the normal out of that too. And just like with the modifier, we don't actually need to use the empty object. We can just use the texture coordinates of the actual tree, the leaf object, and then offset them by the amount to the center of the leaves. So this is subtracting the z distance, the z location of the empty, so that's giving us the same point in space. It's a bit counterintuitive. You might think that it should be added, like if you're starting at 0, then you would add 4.5 to get up here, right? But actually what you're doing is you're telling it that this stuff is down here. So you're subtracting it from its current position, because before that, this is the distance from 0. So we've got position relative to this central point, and then we run it through a normalized node, and that turns it into direction, into an angle. And that's basically the angle that is facing away from this point. If you drew a line from here to here, then perpendicular to that is the normal in that place. So how exactly does it do that? Let's look at an example. If you've been watching my normal series, you already know about this, but I'm going to do a quick visual example. And this is a geometry nodes node group that is going to do that for us. I'm not going to cover how it works, but there it is if you're really curious. So we've got a monkey, and we're looking at its wireframe. And we're going to give it we're going to visualize radial normals from 0. So every vertex in the mesh has a position. In edit mode, you can select it and you can look at it. Here it is in local space, or you can look at it in global space, which is the same in this case because our origin point is at 0. And that position vector is an XYZ. We're used to those. But sometimes vectors are used for position or a location, and sometimes they're used for an angle or a rotation. What's the difference? How it's used depends on the context. If you're plugging it into some mathematical operation that's going to treat it as a position, then that's what it is. If it's going to treat it as an angle, then what angle is that exactly? What angle is defined by this XYZ position? It is the angle of if you drew a line from 0 to that point. So in this case, that would be straight up, that would be +1 on a z. But for this point, it would be from here to here. That would be, well, whatever angle that is, some z and some x. So if you do like this, that's from 0 to that vertex. And then if you do perpendicular to that, this would be the normal of that position. So our GeoNodes example here will let us visualize this. Here is a line from 0 to each vertex in the mesh, and here it is with the mesh. The line is however long it needs to be to get there. When you have a vector, vectors have what is called a length. And the length is the distance that point is, XYZ, from 0. So some lines have a longer length and some have a shorter length. When you normalize a vector, like we were to turn our position into a radial normal, you are setting it to be one length. You are standardizing all the lengths. You are normalizing the length. That's what it refers to. So that would look like this. So now, all of those lines, they still go through that point, or try to go to it, but they're all 1 unit long. The reason it's important to do this when working with vectors that represent angles is that you can have a vector of any length be the same angle. What matters is the direction they're pointing in. So if you want to do math and properly combine angles or rotation information or any of this stuff, it needs to be standardized. Otherwise, the numbers are just all over the place. So that is why we have the convention that normals are always normalized. And when you take position of a vertex and you normalize them, well, what we're getting looks a lot like a sphere, doesn't it? And that's because it effectively is. And we can actually set the Suzanne to have its actual vertex position match where these lines are with their length of 1. And we can see doing that has turned it into a sphere. It's not a perfect sphere because we have limited vertex density in some places, but if it had an infinite number of vertices, it would be. And when we do this in the shader, we're working on a pixel level instead of a vertex level, so effectively we do have an unlimited amount of vertices, because it's doing it per pixel on the screen instead. So yeah, this works with basically anything. You take any mesh, you draw a line from the center to each vertex, then you clip those lines to be 1 unit long, and set the mesh to match that, and you have a sphere. Here's what happens if we normalize the position of our leaves. It turns into a sphere. There you go. In this case, I had to subtract the offset from the origin to the center, normalize, and then add it back. Otherwise, it would move them down to 0. And this is how the cast modifier works, by the way. Except, right now it's doing it to 0, but we've got the spherify option there. So back to the shader, and now we understand what that normalized node is doing and what the normal edit modifier was doing. Okay, next problem. When we rotate, the normals don't change. And that includes when we spin. And remember, this is a problem because these colors, these represent directions in world space. So yellow is Y. So if we rotate this around, now it thinks Y is that way. And the effect of this, if we use it with a shader, is that our shading is stuck to the mesh. We can move it around just fine, and we can scale it just fine. In fact, scaling isn't doing anything, which is not good if you want scaling to do something. And the reason that none of this is doing anything is because all of these object space transforms do not influence the object coordinates. The coordinates are the coordinates within the object space. So since we've rotated it 45 degrees, as far as the object is concerned, X is now over here. So the issue isn't that they're being corrected. The issue is that the changes we make at an object level aren't affecting the mesh at all. Now, if we transform it with an armature instead, it's totally different. So I've got an armature modifier, and here's a bone. And if we rotate that, well, the mesh is moving within the object. The object isn't changing. So now we're just rotating away from the position. And same, if we rotate on Z, it's fine because, it doesn't move away from it. But this is no good. If we go back to our normals from the normal edit modifier, then it is working properly. We are moving the mesh, but we are doing it after the normal edit in the modifier stack. If we do it before, we have the same problem as the object normals have. So the deform of the mesh in the object needs to be after. And of course, with the normal edit, we don't have these object problems in the same way. So the normal edit modifier is already doing things to keep everything working correctly for both object transforms and transforms of the mesh within the object. And we need to implement that for our object setup. Let's fix the object level transforms first. If you've watched my video on generated face normals, then you know where this is going. We need the rotation of the object or any other transforms so that we can properly apply them. Back when I made that video, we had to get them from a driver, but now we have a more convenient way. They are now an object level attribute that is just available from the attribute node. In fact, if you go into your object panel, pretty much everything here is available. Like, we can mouse over location X and we can see this is object.location. And that is the name of this location attribute. We've entered location here. Let's take a look. Move it around. That's the location of the object. And that's the location of the object in world space. This is actually the same thing we get if we use the object info node. This has a location output. But only location. It doesn't give us rotation or scale because this node is old and predates this attribute stuff being added. I don't know if they'll phase it out or if they'll add these to it or what, but at least we have these options now. So we can take a look at our scale too. It starts out at 1. If we scale down, the number gets smaller down to 0. If we scale up, it's going larger than 1, but we can't see that. So, whatever. And of course, here is our rotation Euler, which again, you get the name from looking here. And I think you can get most of this other stuff too. I'm not sure about these various checkbox booleans, but you can get the color and all. So this is the setup here. We are rotating by the object's rotation. And now it behaves properly. Now, how about location and scale? We don't need to do anything about location because normals are always relative to 0 effectively, so we don't need to adjust for anything there. And we don't necessarily need scale, but you might want it. Right now, this isn't really doing anything. This is still going to shade as a sphere even when squished, instead of a squished sphere. I can't even say that properly. But if you do want it to squish, which the normal edit normals do, then you would just multiply by the scale. And now that's going to squish. It's hard to see, but it is. It's doing that thing. Yeah, it's a bit easier to see there. If I do a really big one. And of course, if you toggle it off. There you go. Okay, so object transforms are accounted for. Now, how about other deforms? Those still aren't working because this is moving within the object and the point is defined in object space. So we got to do something about this. Let us continue to descend the node graph down to our next snippet. This is a different formulation of the same thing. It works in object space, and it does not work when deforming the mesh. But it's bringing us a step closer. So what are we looking at here? Instead of the scale and rotation being applied to the object texture coordinate minus the offset to get up here, we're just taking that offset, applying it to that, and then subtracting that from position. And this is important because this texture coordinate is object data. It's position relative to the object. And this position is also position relative to the object, but this is mesh data. And it is mesh data in world space, which is what matters here, whereas this is object space. So these look like the same thing. They're both telling us the position of the vertices. But this is the position of the vertices in world space, so things change as I move the object around. And this is the position of the vertices in object space, so things don't change as I move it around. So that object versus world space position distinction is very important, and it does solve our problem in a minute. But for the time being, it's introduced a problem if we move the object. So now we do want our object location. We're just going to add that. And problem solved. So the reason we still have this problem is that we are defining this point in space here, Z4.578, as the center point. That gets adjusted when we make object changes. It does not get adjusted when we deform the mesh. So we need a way to define the point in the center of all the leaves, even when we're moving things around. And with geometry nodes, we can do that. It's actually really easy. Let's grab that. There we go. It rotates, it scales, it rotates on weird axes, it rotates on, well, Z. Perfect. No matter what we do to this, it's always going to be measuring from the center of the leaves. What I've done is used GeoNodes to get us the bounding box center for the leaves. In GeoNodes, you can have it output the bounding box. Let me stick those together so we can really see properly. And so no matter what happens to the leaves, we now have the bounding box, the furthest point around it, and it provides us, the bounding box node gives us the minimum and maximum locations, the edges of the box. So if we average those, mix them, that gives us the center. So that is what I am outputting with this attribute. And in the shader, that looks like that, which is about the same as that. It's very slightly different. Now it does move a bit as we transform the mesh, but that's fine. And, you know, it doesn't matter if we're making object or mesh level deformations. Everything keeps holding up. It's always just going to give us the point at the center of the leaves, and all of our other stuff is fixing all of the other issues with object transforms. So this is the complete setup. So the bounding box center isn't the only way to do this. We could have some other point where we could compare the undeformed version of the mesh, like the undeformed position, to the deformed position, and thus apply an offset or whatever. There's a bunch of ways you can do it. Bounding box is just very convenient and good for this use case of a tree where we just need radial normals from one point. If you wanted to do like a character with limbs and you wanted to do like this for every limb, that'll get really complicated, although you could technically do it. Now, this bounding box center trick will also work if we're using object coordinates. that's still fine when we're making deformation changes. But then we run into problems when we're making object level changes because we're already canceling out object stuff. So there's not really a combination that works well for canceling object transforms and using object coordinate. So that's why it was important to have the world space position. Also, while we're here, something to note is a lot of these things, like we could get position from geometry nodes as an attribute too, instead of from the geometry node here. And we can also like use geonodes. I've got a group here where this is doing object coordinates from geometry nodes. If we wanted, we could use drivers and get the Lockrot and scale and do this same fix in the geonodes themselves. The reason I haven't done that is because it's not as convenient. And that is because geometry nodes does not have easy access to these attributes, because these are object level attributes. So you can see that we've got them on object. And actually, I'm going to change them to instancer. Instancer means that if you have multiple instance copies, it'll use the instance object first. And then if there isn't an instance, then it'll go to object. So the bounding box center is geometry, position is geometry, but these are instancer, aka object. In geometry nodes, we can input attributes with the named attribute node, but these are only for mesh data attributes, so it cannot access the object transforms. You can get them from the object info node, but only if you select your object in it, or in the group input. So you can do that, like here it's got leaves. If we now duplicate this, it does know it was referencing itself, so it will reference itself again in the duplicate. But I'm not sure if that'll hold up when doing like instancing within geonodes. I haven't tested that yet. The point is, you probably can achieve basically the same setup in geonodes and save yourself some compile time, but it's going to get complicated too, and it's not really necessary here. But maybe we'll come back to that if I do a second video that actually gets into mass instancing these things. So yeah, there's a lot of ways to do what we just did. You can do stuff in the shader level or on the geometry level, and there's kind of pros and cons of both. We're just going to go with this because it's simplest. So I've put everything in a group. We've got our coordinates, which will let us get the position of things relative to the bounding box center and keep with all our deforms. We have our radial normal, and now we can actually use our real geometry normal because I've disabled the normal edit modifier. Before, they were getting sphericized. And we'll want those when we get to the leaf texture. So we're back up at the main setup, and everything looks exactly the same so far, but now it won't break when we move things around or when we duplicate the tree and make a bunch of instance copies. And we have proper coordinates that don't rotate with the tree. They stay in the right position, but they don't get messed up. And we have our original normals. So it looks like nothing much has changed, but now we can get into some real fun. Of course, as my regular viewers know, my idea of fun is normals, so I've made a new group that we can mix some normals in. So far, we've got a noise texture, which looks like that, which right now is not much. We are mapping the noise texture with our coordinates we just made, so that means as we move things, they stay in the same orientation relative to the point they're being projected from, regardless of object or armature deform. So that wouldn't look very good if you're planning on like animating moving the tree in this way, but these are going to be used for normals, so we do want that behavior. If you're going to animate this, you'll have to do some more stuff, but that's beyond the scope of this tutorial. This noise is not usable as normals yet though. We're going to need to do a few things to it. First of all, let's turn down the scale a bit. I'm not really going to worry about like the detail and stuff or the roughness at the moment. But we need to map it into the proper range to be normals, which is -1 to 1. And we do that with good old vector math. So right now it's in a 0 to 1 range. So to get it into -1 to 1, first of all, we subtract 0.5. And you can mouse over and hit Control-C to copy and then paste, which is handy. So now it's in -0.5 to 0.5 range. So to make that 0 to 1, then you multiply it by 2. So that has effectively expanded it to fit the right range. Now that looks more familiar. So we can go ahead and output that in our normals and plug that into our shader right now and enjoy this glorious noisy mess. And if we have the full stack on, well, that's noisy. And it's kind of lost its real shape because we've basically randomized the normals to just point in all sorts of crazy directions. Now remember, this remap to -1 to 1 is critical for this to work properly. If it is in 0 to 1 range, well, 0 to 1 corresponds to only the positive values on each axis. So that gives us normals pointing in only these directions, like only this quadrant of the grid. So if we want this to point in all possible ranges, then you do need that remap. And that is what we want, because what we're going to do is take our sphere normals, which I didn't bother passing in because we can just make them again, and we are going to mix them with this noise. Now, when we play with mix factor, we are introducing some bumpiness into our shading. It's kind of like a bump map, actually. In fact, if you had plugged the FAC of this noise texture into a bump map node, you get basically the same effect, except it would actually be lower quality. Now, we're only going to want a very small amount of this, and how much we want kind of depends on the scale of the noise. Let's turn that down even more. Because my goal is to kind of break up this visible, like, just solid band. So a little bit of noise goes a long way in this case. We'll just do 0.1. So that's quite noticeable on the sphere, on the tree not so much. So you kind of have to judge the right amount. We can move our light around a bit and check it out. It's starting to look quite good, I think. Maybe a little bit more. Let's try 0.15. So this is where you actually make artistic decisions. To make that a bit easier, let's turn this into inputs. And we might as well get the scale in there too. Because part of the point of doing all this is so that we can quickly test things and see what it looks like. What about like a high FAC at a very low scale, like just a little bit of waviness there? Anyhow, you'll have to play with that and decide what you like. I'm going back to these values for now. So if we want to duplicate and instance these trees, I'm copying with Alt-D, so it's an instance duplicate. The noise is the same on both, and we can't have that, so let's get some randomness in here. We can use object info and random, but where do we put it? We're going to use 4D noise, which has this extra input, W. W is also called phase, I think. So this changes the noise pattern, because W is time, the fourth dimension is time. So we do that, and now they have different noise patterns once it compiles that. There we go, they're different. I'm going to make the noise a bit more interesting, like I did in my previous setup. We're going to add that. And we're going to make ourselves a random seed input, just so that we can control this from outside the group. We don't need different random values per leaf in this case. One value for the whole object is fine. So we'll wrap that, plug that in there. And these compile times are really starting to add up, which is how you know you're watching one of my videos. But I've cleaned the group up. I've put roughness as an input so we can play with that too. But overall, yeah, this mixing noise into your normals is a nice way to kind of break things up a bit. It's broken up that spherical look, which is exactly what I wanted. So that's a fairly easy and low effort way to add some detail. Now let's look at another way of adding detail to normals that is complete black magic. So I've got a normal map texture of my leaves, which is part of why I modeled them as geometry, so I can make this. And here's what it looks like. I've got the same randomized tile set up as on the alpha texture. I've projected the sphere's normals from the front, and I've got this other plane just so we can preview it easily. And on the leaves, it's kind of a mess. And we can run it through a normal map node, and now it is normals, and it's still kind of a mess. We can make it somewhat less of a mess with our invert normals on back-facing trick. That helps. So like on this plane, now it's the same on both sides, and it hasn't changed the sphere because that's not a back-facing, but it's a bit less of a mess. And we can go and plug this into our shader if we want. And now we have all this crazy leaf detail. It's pretty advanced, actually. And it's not very useful because the normal map is on top of the mesh's base normals. So a normal map like this is called a tangent normal map. It takes the information stored in the normal map here, and it rotates your normals by some amount based on this. You actually remap this. This is a value between 0 and 1. You remap it to -1 to 1, and it is the amount to rotate your base normals. The normal map node is hardwired to use those normals and to do the rotation based on tangents, which are based on a UV map. I haven't checked this because it defaults to your first UV map. So that all works fine as long as you're using your basic mesh normals. So how do you use a normal map with custom normals or our mathematically made normals? And normally you can't. It's not really a supported feature. The normal map is hardwired to certain your base normals and their corresponding tangents. And if you have a custom normal, like from our normal edit modifier, it will work, but there's actually a bunch of distortion. It's hard to see in this example because it's just a leaf and we have a ton of them. But you can see like this is kind of fuzzy. That's not the proper shape. We'll be able to see a comparison in a minute. The reasons this happens are complicated and technical, and I'll be covering them in my big normal series. But basically, the base normals and base tangents have to be matching. They correspond to each other. When we do a custom normal, like the normal edit modifier or data transfer or vertex normal editing, that changes the normal but not the tangent. So then they don't line up correctly and things don't map quite right. But we can get around this problem. So we'll turn the normal edit off and we'll grab this group here, normal to surface gradient. It takes a base normal and it takes a custom normal of some sort, and it outputs this. So the base normal looked like that. Let's use our plane here, or our sphere. The normal map version is that with detail added, and what the surface gradient is the difference between the two. This isolates only the things being added by the normal map, but in world space instead of in tangent space. Next, we have this other group where we put in our surface gradient, and we put in whatever normal we want, and it adds that difference onto that normal instead. So now we can use this in our shader and have the full quality without distortion. And if I toggle the normal edit modifier on and off, that introduces the distortion, and now you can really see the difference. So this is how it's supposed to be, and this is what happens when your normals, your custom normal doesn't sync up with your tangents, because Blender does not have custom tangents. If I put a normal edit modifier on our plane here, you can really see how badly it butchers it. So surface gradients are just amazing. It allows you to isolate bits of normals, offsets of things, differences between things. You can use these to combine multiple normal maps. If you had multiple normal maps on the same thing, you get the surface gradient of both. And then you can just add these together and then run it through this. So they're super powerful and versatile. And we can even do this on top of our normal with the noise in it instead. Because it is just stacking that rotation. Now, this is a bit too strong, so let's tone it down a bit. we could mix this back with this, but we can also just mix the surface gradient with 0, because 0 does nothing. And we're really stacking up those compile times again. So that shuts it off completely. So this is another case where we probably want only a very low value just to bring in a little bit of that detail. But now, up close, we've got a little bit of actual leaf detail going on. All right, that's cleaned up now. I've stuck the normal map texture and the initial surface gradient conversion in this group, detail surface grad, and I'm using it in the normal mix group here, and I've added a factor, which is just multiplying it, and that's a separate output right now, so now we can scrub our detail level on and off. I'm not really going to go into how this works in this video. Here is the group to take two normals and get the surface gradient of the difference. It's not very complicated, but it would take a while to explain exactly how this math is working and why you need to do this. And, as opposed to other ways of getting differences or mixing. And the group to actually use it is incredibly simple. I will be going into detail on how all of that works in my next Customizing Normals video, though, so check that out if you're interested. But here I will show you how I created the leaf normal map. So the reason I modeled my leaves out as full geometry instead of just drawing them was so that I could go back and get normals or AO or whatever else I might want to do for them. So how do we actually get our normals baked properly to a normal map? Well, the answer is that we don't really. And I mean, if we go to cycles and try to bake with the normal bake system, it's just really annoying to do it properly. You make a plane, you select everything, you have to set up a texture to bake to on the plane and all that, and then you have to get extrusion correct, and it's really a hassle. You can do it, but it's hard to just get it done without distortion. What I want is something as simple as what I showed for the original alpha mask, which was just, they're already flat, so I just want to render this. So I've just made a setup that lets me do that. A tangent normal map is the difference between two sets of normals around the axes defined by the tangents. And I'm not going to explain what all that means here. I will be talking about that in a Customizing Normals video at some point. But basically, I just made a node group that just gives you in the viewport exactly what you would get if you were just baking these. And then there's an orthographic camera with very simple settings. Size of 1, because my whole object plane is set up to be 1 by 1. Got my reference bounds. And then I've added this bake plane to fill in the background color. So then you just F12 render that, and that's your normal map. That's it. No baking hassle. And the reason this works is because we're working with something that is already flat. You do want to make sure that you save it out properly and don't have any color management. Make sure your view transform is standard, not filmic, because this color information it represents mathematical information. It's vectors, it's not color. So when you save this, you want to make sure Save as Render isn't checked, because that applies color transforms. And you want RGB. You should be fine with either 8 or 16-bit. Do 16, 16 to be safe. I haven't really compared it. This is the same thing as when saving regular baked textures. You have to have enough bit depth to contain all the normal information. I will also be talking about all the details of the right formats and bit depth and everything like that for normal maps in some future video, but I'm not going to cover all that here. The background color does need to be just right. It needs to be 0.5, 0.5, 1. And this can be a bit tricky, because watch this. If I copy this hex code, and then I paste the hex code, it's actually off by a tiny bit due to, I don't know if that's a floating point error or something to do with how the hex code works. But you are going to need to manually type in that 0.5. I don't know if you can eyedropper it right either. So I guess I need to re-render this because I didn't have that correct in this setup. I'm not going to try to explain this entire tangent space difference group here either. Here's what it looks like inside if you want to build it for yourself. It's a bunch of vector math. The really quick version of what this is doing is, so the surface gradients we looked at before gave you the difference between two normals in world space. What this does is it's getting the difference between two normals in a tangent space. The tangent space means instead of x, y, and z being what we're used to, it's x, y, and z relative to something else. So like if you go into edit mode and you start transforming something in global space, then when you lock it to x, it's, global x. And instead, if you lock it to normal and then transform an x, it's x for the plane of the face, or, y for the plane of the face. And that's essentially what tangent and bitangent are for. So x, y, z in global space are the three axes. And then in tangent space, x, y, z are defined by z is the normal, and then x is the tangent, and y is the bitangent. So yeah, all of this is just rotating things by some amount, but in some axes relative to the face instead of relative to the world. That's what a tangent normal map does. So what these inputs here are is defining what those other axes are. And in this case, it's very easy because we've got our leaves and we're comparing, we want the difference in rotation between essentially the leaves and a flat plane, which is pointing up on z. So 1 on z, that's just pointing up. And so we're telling it the z-axis is actually world z. And in this case, we're telling it that the tangent, which is the x-axis, is 1 on x, which is just the world x-axis. And then the normal is the actual normals of the mesh. So that's our input. It's very simple. This could be a different object, but what makes this easy to use is that we're getting the difference in tangent space between these and flat, and our tangent space is the same as our world space. So that's why we don't need fancy baking that's really comparing the meshes in a complex way. We can just easily, we don't need another mesh as an input here. We don't need to transfer normals before we can compare them or anything, because we're just comparing it to flat, and we know what the normal for flat is and the tangent. Anyhow, we'll save the rest of tangents and normal maps for a later video, but the point is, if you just want to take a snapshot of detail that you model flat and just get a normal map of it without going through the whole obnoxious baking process, just build this group and do exactly this with these inputs, assuming it's pointing up on z. If you had it pointing, this direction down y instead, then instead of 1z, you would put -1y. It's whatever direction is facing your camera. And then that's it. Our next big topic is density. And let's start with the actual mesh density before we get into faking volumetric density. So I said at the very beginning that I probably had more leaves than I needed. And if we look at edit mode, I really have a lot of redundant leaves. In fact, I have 26,000 leaves. You don't need that many leaves. How many do we need? That's a great question. I don't know. I just make the shaders. I'm not actually a tree expert. So I've made a bunch of copies with less leaf density so that we can just look at them and make some informed decision. The difference here and here isn't much, except around the edges where things have gotten a bit too few. And I did this by just selecting everything and doing a select random with a 0.5 ratio. So that gave me half the faces. And then deleting that, or some other ratio. So that's how I got down to 13,000. And that doesn't mean you deleted in a very good distribution. So the problem with these comparative meshes is that the distribution of leaves is not good. It would probably be better if you were making it with a different leaf setting in sapling or whatever you make. But basically, we need some amount of density before the shader starts looking a bit weird. Like here, yeah, it's weird at the edges, but it's also weird inside. And this one is still pretty solid inside. So I would say you could have a lot less than 22,000 leaves. You could probably take it down to, 6, 7, 8,000 at like the highest. And then if you had a better distribution other than just random, you could have significantly less. And there's a lot of other optimization things you can get into, like replacing the interior of the tree with spheres with leaf textures on them instead of planes. That's called using shells. Or you could have something like if you're generating the trees for a certain camera angle and it'll only be looked at from the front, then you can just delete the back or something like that. Or, if you want a really low poly tree, you take this tree and then you bake it to a texture and you can still use our normals on it because they're being projected. So there's a lot of stuff you can get into that's really a subject for a video on instancing and optimizing the tree. I'm not going to get into that here. We're just doing the leaf shader, but I wanted you to know about it, that what I've done here is excessive because everything I'm doing here is excessive. Next, let's look at shader tricks to imply more density and volume to this tree. We already added some noise into our terminator to imply a bit more shape, and we've got our terminator position less than the usual 0.5 in order to imply some light passing through. But since we have our coordinates, we can get basically the full volume of our big cluster of leaves here, and we can do a lot with that. Here's a new group we can work in. We're going to take our coordinates, and the basis of a lot of this is going to be the distance node, which at first appearance doesn't do anything, but that's just because our values are so much higher than 1. But check this out. Let's normalize our coordinates, which gives us our typical normal, remember, and get the distance between the position coordinates and the spherical normal. Now what do we have? It's a bit hard to see because our transparency isn't on, and I have so much leaf density, but if we start mapping that range a bit, we can see that what this is giving us is a gradient from the center out. So it's 0 at the very center, out to 1, depending on what range I map this to. So this means we can mix things based on how far they are from the center of the tree. And since our tree is spherical, that's basically simulating density. So for example, we can make it brighter to the edges, or we can desaturate even more, or we can adjust the hue, or any sort of effect we can think of, or we can apply this as a mask for any of our other effects. For example, here I've set it up to mix between two values for our ambient strength. So at the center of the tree, we can disable the ambient light. Completely disabling it is probably too much. It shouldn't go black in there, but generally there should be less ambient light getting into the middle. So maybe we'll have at the outside it gets 0.2 and in the center it's only 0.05. So that's adding a bit more dimensionality to our tree in a very simple way. Or we could adjust our terminator position a bit. A major change on that will probably look weird, but a bit of subtlety is essentially darkening up the middle again. There's always just directly applying it into the shading. The darken effect causes it to use whichever one is darker, but unlike multiply, it won't make things darker than the darkest value. Too much of that is bad, but again, a little bit of that. How about something really weird, like steps based on it, if you wanted to stylize the tree that way, or whatever. That's steps, and then still using the darken. Pretty funky, but who knows? There's just a massive amount of possibilities here. And it doesn't only have to be shading and colors. We can mix our normals based on that. How about no detail effect in the middle, because you don't really need leaf detail in the middle, but then turn it up at the edges. That kind of brings it a bit to the foreground from whatever angle we're looking at. Or we could do the noise. You don't need as much noise in the middle, and more at the edges. I don't know. I don't know what looks good. I haven't played with this that much, but you should try it out and see what you can think of. Whatever we end up doing with it, we probably don't want it to be too linear. So that's where we could color ramp it to, ease it, or we can make adjustments on the color ramp or in the map range. There's also like RGB curves. We have the float curve here, which is perfect for this. If you wanted to, like raise it a bit here and lower it a bit there, or, whatever you want to do, this is the place to really look into all these ways that you can adjust things with the mask. And of course, this isn't our only mask option. We can also just take the coordinates and, separate X, Y, Z and turn these into masks from some range to some range. And this reveals an issue we may run into problems with, which is that we are manually defining what ranges we want to use. So we know the X dimension of our mesh is 7.308. So if we wanted to make this from this point to like that point, then what we would do is make it from that divided by 2 to that divided by 2, or minus that. And now we've got black all the way to white across the x-axis. And we can do that with any of these axes. Now this isn't 100% precise because this dimension is from here to here. So it's precise if it's exactly the same size on either side of the x-axis. But it probably isn't, so, it's not going to be entirely precise. But it's close enough because our tree is spherical. If the tree was some more complex shape, then getting masks of various different parts of it would be more complex. So that's another reason we started with this one. And since we are defining our mapping size in world space here, we could run into problems when instancing this tree if the size is very different. There are ways that can be fixed by getting more information from geometry nodes or like normalizing the coordinates to 0 to 1 before using them. And I'm not going to talk about that because it would be like another 15 or 20 minutes. So we'll leave that for if I do a video on actually instancing and duplicating trees. For now, I'll label this center mask. I think 2.5 is a good amount. But let's also get a mask from the bottom up, because density generally doesn't just occlude from the center. Since the light is probably coming from the sky, we'll do some fake occluding at the base. Could adjust these further, but I think that looks fine for now. And I'm clamping both of these so that if I'm ramping them more later, it doesn't cause any issues. I've created an output for the center mask and the lower mask, because I'm not exactly sure what I'm going to do with them yet. But I also want the two of them put together, a combined mask. And this is a good place to use the darken node, because it gives you the darker of the two values. Whereas if you use multiply, then areas where they're both dark, it doubles the darkness essentially, and here it doesn't have as large an impact. You could use whichever you feel is appropriate for what you're trying to make though. And I guess I can do this and save the compile time. Oh, and before I forget, I was using this mixed value node before. This is just a mixed color node, but with value input sockets so that you can type in a value without having to add multiple value nodes. So that's all that is. I'm not going to use these masks for anything quite yet, because there is one more way we can get some density information, and that's good old ambient occlusion, which does not work until you enable it here. Ambient occlusion is great because it will get us some more occlusion in our leaves, and we can even use it with our custom normal to make it a bit more spherical. But there is something you have to watch out for. Let's get a diffuse shader. And we'll use our alpha so we can see it a bit better. And I have disabled the sun lamp. And let's go over to world and turn on some indirect light. That's our only light source. But we're getting AO on it. So the ambient occlusion node doesn't work unless you enable ambient occlusion in render settings. But once you do that, it automatically applies these settings to any use of the diffuse shader, and I assume other shaders too. So if you are using a version of this setup that does use a diffuse node, or anything similar, then you need to turn that off by turning all that down. And there can still be some artifacts, so you really have to turn everything here off. If you're not actually using any world light though, then there's no problem. So what we're going to do is basically implement the same thing that AO is being used for on the actual world light for actual shaders, but for our ambient strength over here. Keep in mind, though, that some of these settings do affect the behavior of the node. I think bounce and bent normals don't, but trace precision does. It's a bit hard to see. We'll look at it when we have a better example. So This is part of why I'm just not using the world light at all again, and not using real shaders. Just another bullet dodged. So I've made a group to put the AO in as well for organizational reasons, and I'm going to darken it with the density mask, and then I can remap it. And what's a lot of fun about AO is you can also give it a custom normal. So with just the base mesh normals, it's not much to look at, but here is our radial normals. And what I've decided to do is that my Lambert shading, my actual shading, is going to use just the radial normal and not get any of the normal map detail. So I've changed what was previously the detail version over to just the AO normal, and also changed the name of the FAC. When we turn that on, we can see that our AO is getting the normal map. So it's picking up some of that shape from the normal map. The reason I've chosen to do it this way is because I think the normal map was just too strong on the main shader, and it's probably not really necessary at all, but, you know, I wanted to show it, so I've thrown it in the setup, so I'll just use it here. But this is a fairly arbitrary decision I'm making. Just like the density masks, we can use the AO for pretty much anything. The obvious thing, of course, is to take it and multiply our ambient light by it and kill the ambient light where the ambient occlusion occludes it. And I'm going to turn the occlusion from the density masks on. But this is a bit too strong. I don't want to completely murder the ambient light everywhere. Otherwise, you know, the scene could be very bright, and that's always going to end up 0 where the AO is black. So let's remap this a bit. Now it's 0.5 to 1. So in the areas where the AO is darkest, it's only getting rid of half the ambient light. So that gives us a bit more detail in our shadows, which I like. Density mask may be a little too strong on the AO effect. Let's make that 0.5. Because this is where they're coming into the pipeline to then be multiplied over the shading too. Yeah, I'm not sure what I want there. 2/3. Let's do even more with our AO and density. In our combined colors, I've added at the very end a soft light node, which does this. To understand what soft light does, let me show you overlay first. So as we turn it on, in areas where the AO mask is dark, everything gets darker, and where it's light, things get lighter. And the reason that I've mapped the range from 0.51 to 0.1 is because, remember, our incoming AO was already mapped to be 0.5 to 1, so it's really bright. If we don't have the map range doing anything, then we're only seeing brightening effects. This is because overlay is either darkening or lightening based on if the mask is a value above 0.5 or below it. So right now, everything is above 0.5, so it's just brightening it. And when we remap it properly, now it's the full range, so some areas get lighter and some darker. Soft light is very similar. There's a bit more to it, and I don't remember all the details, but basically it's darkening where your input is dark and lightening where it's light. It handles color a bit differently, and it is, well, softer. There is also linear light, which again is similar, but it's way too strong for what we're trying to do here. So you can look up the details of how the math on these works if you want to know more. Now in this case, I'm not going to remap it. I do want it to basically just brighten. And that is because we're already getting detail from the AO in the darker areas by cutting down the ambient light. But we don't see so much of that in the brighter areas. With the soft light, we do. Now I could use a similar effect. I could do like a division or add or screen, which would do much of the same thing. But this is already working, and this will keep working with various other settings. And yeah, I mean, you can do pretty much everything in more than one way. So right now, this is brightening up my darks too much. So let's mask it based on the shading gradient. I'm going to go through this mix node just so that we can control it properly. So now we are brightening things up, but not too much in the shadows. Still a little bit, but not much. And we probably want a pretty low FAC on this, because you can see how much it's doing. Too strong of an effect will make our object have too much detail. I want just a little bit for close-ups. And like when you're further back, you're not really going to notice this anyway, or we may disable it further away. I've added a multiply on the shading gradient to control how much to do it. I think I'm going to go for just a third. That looks like a good amount. And this could become a FAC input on the group, but I think it's fine just like this. So that's given us a little bit more nuance in our light areas based on the AO. So AO doesn't have to only be about darkening. I think that's all I'll do with the AO in this setup, but I've also decided to use the density masks to make the noise inputs a bit more interesting. So I changed up the outputs in the density group because I was only using the combined, and I'm using it as a mask for scale and roughness. These are the values I had before. So the first number is closer to the interior of the tree. Let's try a really low number and see what that looks like, and make it a bit higher at the edges. Cool. And then the second one, the roughness, maybe rougher or less rough at the edges. I guess it should be less rough in the center and then rougher at the edges. So these are really subtle changes that I'm just kind of doing for fun. It's not visually that visible. Maybe I should do something bigger to really have it be noticeable. But whatever, you can play around with it. And speaking of small features that are only really visible up close, sometimes you want to make sure you turn those off further away. So for our last feature, we're going to be looking at Z distance. In stylized styles, generally things that are far away are not very high detail. And to some extent, this is already losing most of its detail when we zoom out because it simply gets smaller. But there's still quite a bit there. There's more than you would have if you were, say, drawing this and it was that far away. Also, the alpha kind of dies if you get too far away. So let's add a control that lets us turn off some of our effects the further away we go. View distance tells us how far something is from the camera. And I call it Z distance sometimes because it is the Z axis of the camera vector. Also, with orthographic on, it doesn't really work. You need to be in a perspective view because orthographic kind of by default has no Z distance. And right now we can't really see anything because these are real world values and our tree is pretty far away. It's at 0, 0, 0, and right now our camera is at -36. So it's just too far off to actually see what's going on. So of course we need to map the range. So we've got a map range node. I've stuck the inputs out here. So what did I say the camera was? It is at -36, so 0 to 36. And there is data about the tree. So there's a couple ways we can use this distance. One would be to get like a normalized mask of the part of the tree closest to the camera and a gradient to furthest. For that, we would need to get the camera's position and use that to map things. I'm not going to go that far. But, if you know the camera position and you know the tree position and you know like the bounding box for the closest and furthest, all of that information can be gotten like from geometry nodes. We can get the bounding box. We've already got it. So you could build that if you wanted a normalized distance pass upon the tree. But I'm not going to use it that way here. I'm going to just set it up as a way to control certain effects coming on and off, depending on how far away we are from the tree. Let's unpin our sun, and I'm going to pin the camera so we can keep track of its distances easily. Right now we're at -25, and I've hooked this up to the noise mix FAC for the normal. I had that noise FAC at 0.15 before. So the way this works is when we are at 0 distance, this will return 1, and then once we get to 36, it will return 0. So let's set this to like 1 and 0. So when we're up close, we have the full FAC of the noise. As we zoom out, it turns off. And it's fully off by the time we get to 36. So now we ask ourselves, at what distance do we still want to be fully on? I think I like my 0.15 noise out to about here. So that's 43. So we're going to start this at 40. And then I want it to be gone by, let's say, here. So that's 90. 40 to 90. And then we can set that to 0. And now we have our 0.15 noise as long as we're within 40. And as we get further away, eventually it is gone. But it's a pretty subtle effect, which it should be. I think actually I'll make that a bit stronger. I'm going to change that to 20 and then change this to 0.25. So now it's even stronger, very close up. And let's have it be gone by 70, I'd say. So that's pretty good. So now we don't have quite as much visual detail on the noise at this range. Before we had that much, and now we have that much. I've moved the mix value inside the group and renamed some things, but technically we don't even need this. We can just define these values here in the 2min and max. Now note that currently this is going 1, 0 instead of the default 0, 1. That's why it is white when we're right up against the object and black when we are further away. I chose that behavior. The default would be 0 when you're 0 distance and 1 away. And that's because it seems more intuitive to me for the noise min to define the value up close and the max to define the value far away. But you could just do this instead and reverse these. And it's the same effect either way. It's just a matter of how you want to format the values on your group for the user interface. Actually, I'm just going to rename it to noise close and far and reorder those, and nobody has to know. So now it's the most user-friendly. And we'll put 0.25 there and rename those other inputs, and we are looking good. I've set one up for the AO normal detail as well, so now it's at full strength up close. Then once we get to 15, it starts interpolating down until we're at 35, and it's all gone. But there is a problem, which is if I keep going, it comes back, but it's inverted. And this is an issue with the map range node. Things are basically wrapping unless we clamp. So that fixes that. So you can use this to control as many of the various features we've built as you want, or you could just mix to some totally new thing. Like if you wanted to eliminate almost all of them, you might want to have it be that when you're this far out, that it's just a single shader with just maybe the color shift and nothing else. So you can set this up in whatever way you like. I just wanted to demonstrate the concept. I've added one more that is just mixing here, which ignores the saturate and the brighten with AO and just goes back to the regular shader. So that's, again, reducing detail a bit as you get further away. I didn't bother setting that up with inputs because whatever. Also, I did have the noise valve close and far. I had the name switched. Yeah, so there's a ton you can do with this if you want to. Keep in mind that this is only an artistic level of detail change. This isn't like a LOD for performance. You're still stacking up the full shader. In fact, this is a more complex shader. So if you were using a proper LOD system with different versions of the asset that were getting turned on and off at different ranges or something, then you wouldn't need this. This is purely an artistic thing. Also, keep in mind that these are all linear effects right now. It's all linear gradients. You could put these onto like smooth or smooth step. You can step them. You could put them through RGB curves to change up how fast things go on and off, or color ramps. You could do more complex mixes to go through multiple different effects, whatever. Okay, I think I'm ready to call this done. We've thrown a ton of different features into this shader. They're all in these different groups. I've set it up this way so that it's easy to see what we're doing, and so that if you want to try using this, it's easy to just take some whole part of it out. And you probably should, because this is really heavy and slow in compile time, and we've basically got enough features in here for a high detail up close tree, which this isn't really intended for. And we probably don't need this many features when you really, are instancing like a whole forest and you zoom out. Of course, the reason we went through all this stuff was just to teach you about a ton of different things, get them on your radar. You can use them where you need. I think it's pretty neat that we got all of this done and have all this detail in it, and we actually only used one shader node. Normally when you see fancy shaders, there's like a million textures and shader mix and, principled, SDF, gloss, and all that stuff. But I guess what I wanted to demonstrate here is that a lot of shader art is just about the things that come before the shader node, not necessarily the node itself. Or in the case of NPR, it's just mixing different things based on various different input properties. And since we built this spread across a bunch of different groups, it's easy to take out parts that you don't feel like using if you actually intend to use this tree shader, which I would suggest restructuring it a bunch first. In the file release, I am going to put in a copy of this material where it isn't all in groups. It's going to be just one thing, because otherwise you're going to have a ton of group bloat in your file. I've got all of these, and then we used a bunch of these, and then I have earlier reference versions that I've been looking at as I recorded this. So yeah, I'll put that in. Now, I assume that some people watching this are here more for the tree part than the just like esoteric shader stuff. So the next question for the tree enthusiasts is, well, how do I make this into a forest? How do I actually use this with an instant setup? And I have experimented with that. I've been trying to build this whole thing with that in mind. So here's a collection where I've made a bunch of copies of the tree. These are instanced copies, so Alt-D to make more of them. And it works just fine with these. I'm just manually giving them, some rotation and scale differences. And the shader we've built is perfectly happy with this. Now, if you really want to get the most out of scattering and procedural generation, you're going to want to use geometry nodes. So I've included an example of that because I was playing around with it. So I've got this grid, which has been kind of scrunched up just to get some randomization. And it's spawning the trees based on that grid. Here is the geometry nodes for that. So it's inputting the instance grid and the leaf object. It's transforming some things. Actually, I don't think that's even doing anything right now. Yeah, this is all beyond the scope of the video, just to give some idea. So it distributes a bunch of points on the grid, then it instances copies of the leaves on the points. I've only set up with the leaves, not the trunks right now. That needs to be solved, and it works. There are still some issues, though, that would need to be sorted out. Like here, remember, we're using object location from an attribute, and here I've got it set up with the node. Because if we use the attribute, it's doing it for the whole object that the tree is instanced within, whereas this node is using the object of each instance, because under the hood, instances are their own object, effectively. So you need to feed more information from geometry nodes or figure out what this is, and same thing probably for some of these other attributes. So we're like halfway there. This isn't a complete setup, but it's most of the way there to working with mass scattering while still keeping our object and like position generated normals. Or of course, if you just approach normals in a totally different way, then you might not have this problem. So, there's a lot of factors in this, and you can do things in like 5 different ways, which is part of why it's difficult to figure out. So I may do a video about actual scattering and stuff at some point in the future, but it's not going to be a high priority for a while. What I'd like to make in the long run, because I do want to be able to do like nice trees, is something with a bit more granularity. So like right now, this is one blob of leaves that's getting copied, but even with some randomized transforms, it's a bit too similar. What I think would be fun to make would be a tree where like you're instancing every branch. It's a branch level instancing with its own normals. So that could have more detail and support more tree types beyond a sphere. And then that could have enough variety. There's a lot of people who are like working on procedural trees and generated stuff in geometry nodes though. So I wouldn't be surprised if one of them just comes out with a better tool before I really get into this more. On our instance trees that we made manually, this location issue doesn't exist. It's only on the geometry nodes version. So I've made a copy of the leaves with a copy of the material, which isn't node group based. It's all one big group, and that looks like this. So this is if you actually wanted to use this, I suppose. And it's pretty crazy. Yeah, when you remove the groups, you realize just how much stuff we've put here. So all of this stuff I'm going to check up on Gumroad. So if you want to save yourself some time building any of this stuff yourself, or if you just like my content and want to make a little donation, I'll put it up for a couple of dollars. And if you are following me on Patreon already, then I'll be sending out a 100% off the Gumroad code as usual. And as always, feel free to leave comments or questions here, or in the video description, there'll be a link to the blog post for this. You can find my contact info there or on the YouTube About page. You can email me, direct message me on Facebook or Twitter, whatever. And of course, there is also Patreon. Thanks for watching, and I'll see you in the next video.